Thank you. I would like to thank the organizers for giving me the opportunity to be here. It's a pleasure to be in such a beautiful place. And I've enjoyed the talk so far so much. I have to apologize that my talk is on slides. As you'll see, there's a lot of big theorems with lots of torsion subgroups listed that it would just take me too long to put on the board. But my slides are already up on my website, so you can see the notes there. Okay, so there's been quite a lot of progress in the recent past on the classification of torsion subgroups of elliptic curves. So I would like to give a survey of what's been done, so you know where we are, where we can classify all the possibilities that can happen. Of course, the beginning point is Mordel's theorem that there is that the rational points on an elliptic curve are finitely generated, and then you have the torsion. The torsion subgroup, that's what we're interested in, but or that's what I'm going to be talking about. But more generally, we would like to understand the entire Mordell-Weil group and what are the possibilities for the Mordell-Weil group, and I would like to give a talk about that, but there's not a lot known in that regard. So more generally, so I will concentrate mostly on elliptic curves, but one can talk about the Mordell-Weil theorem and about abelian varieties over a number field, and then talk about the possibilities for the Mordell-Weil group there, and talk about the possibilities for the torsion subgroup there. And even more generally, you can talk about any field that is finitely generated over its prime field and an abelian variety, that's the Mordell-Weil, and then the generalization by Neuron. It also says that that's finitely generated, so you would also like to have a classification of what can happen for different fields. That, by the way, it took me a while to find that picture of Neuron. There are not that many online. If you have any other better pictures, I would love to have one. Okay, so the Mordell-Weil Neuron theorem leads to a natural question, which is what finitely generated abelian groups happen for abelian varieties over global fields. And there are a number of ways to interpret this question. In the broadest sense, sort of in the inverse Galois theory kind of problem. So if you give me a finitely generated abelian group, does it occur? Then the answer is yes. There's actually a paper by Pete Clark. Well, let's say no, in that you know what happens to the torsion part of the group. If it's coming from an abelian variety, then the torsion part has dimension 2G as a finite abelian group. But then besides that, if the torsion part can be sort of embedded in what we know the torsion can be for an abelian variety, then any such group appears. For some, if you fix the field F, then there's going to be some extension where these finitely generated abelian groups appear. But that's not what I'm interested in. That's just saying, like, well, they appear, but we would like to know if you fix the base field, if you want to do just what is sort of like the minimal fields of definition where these structures appear. So it depends what you want to vary, that the question becomes more interesting. So for instance, you can fix the field F, and then you want to understand where all the possible Mordell-Weil groups that appear for, say, elliptic curves, one-dimensional abelian varieties over F. So by these sort of graphs, I mean, this is what I fixed, and this is what I'm varying. You can think of all the elliptic curves over F, or you can maybe restrict to certain favorite families of yours, quadratic twists of a curve, twists of another kind, elliptic curves that have certain other invariants fixed. There's a number of ways that you can think about this. Another interesting way to think about the variations is if you fix the elliptic curve, and then what varies is the extensions of f. So over all possible finite extensions of your field f, what sort of torsion happens, and when does it happen? If you know you're going to get points of order p, what's the smallest such extension where you would see that point appearing? And then again, you can change the elliptic curve E at the same time and change both E and F and see what can happen in that case. As I said, in that generality, that would involve, for instance, knowing just even the rank, what ranks can appear if you fix a field F, what ranks can appear. If we're talking about global fields, in the function field case, there's a little more progress on like what ranks can happen. But if you go to just number fields, just over Q, we don't know what ranks can appear. So this part of the question is hopeless at this point. So I'm going to move to torsion soon. But just to say that there is a lot of interesting questions that happen in this case too. For instance, if you fix the elliptic curve f and then you go in extensions and see how the ranks change, then there is a lot of very amazing results that come from Iwasawa theory, for instance, of what can happen with the rank. So there's a lot of interesting questions that can happen in that setting too. But we're going to fix, for this talk, we're going to talk mostly about torsion subgroups of elliptic curves. So that type of variation, fix the field f and change the curve, or fix fields f with a certain invariant. And also, if you fix the elliptic curve f, elliptic curve E, then look at the possible torsion subgroups that can appear as you change in extensions of f. So if you fixed already Q, that's already a very interesting theorem of Barry Mazur. In 1977, he proved what was conjecture of Levi, and then conjecture of Ogg, of what was the list of possible torsion subgroups. And that was a breakthrough by Mazur on the bounds on what isogenies can happen over Q, and that was sort of like the final milestone to complete this classification. And those, of course, they all happen, and they all happen infinitely many times, because the modular curves that parameterize elliptic curves with these structures, they're all genus 0. So if there is points, then there are going to be infinitely many points. And for instance, the curve that appeared in the title screen, that's an example of an elliptic curve with a point of order 12. That's not the smallest such example, but it's one of the prettiest examples as you try to graph it, the point of order 12. As I said, you can parameterize all the elliptic curves with these structures. They're genus 0, so they are one-parameter families where you can find them all. Okay, so let me just, for a couple of slides, talk about really in the Neuron Generality. So what happens if you talk about function fields? So you can fix your function field, say, a genus 0 function field over a finite field of p to the n elements, and then change elliptic curves over that function field and see what torsion subgroups happen. There were results, very strong results on what can happen, but actually I had never seen sort of like the equivalent of Mazur's theorem, what is a complete list for every p that can happen. So that's Bobby McDonald's, that's my student, one of my current PhD students. And so he's worked out what can happen. Cox and Perry had made a list of what are the torsion subgroups that can appear as prime to p part in a function field characteristic p. And Levin had like very nice bounds of what can happen with the p torsion of the p primary part of the elliptic curves. But as far as I can tell, nobody had married both results and come up with a list of exactly what torsion subgroups can happen. So that was part of Bobby's thesis. And you can see the possibilities that can occur. Not all of those occur for every P. The only restriction really in this list is the one imposed by the Weil pairing, that you need, if you are going to have full 5 torsion, then the 5th roots of unity need to be in your field. But as long as that happens, they all happen, and they all happen infinitely often. And as such, you can also find parameterizations of those structures. So this is a table of examples of some exotic torsion structures that do not happen over Q. All right, so he's also worked out, or almost worked out, there's a couple of computations that are still running, but this is if you now change your function field to be the function field of a curve of genus 1, then he can also list exactly what are all the torsion subgroups that happen over a function field. And not only that, now some of these, there are restrictions, and it cannot happen just for any function field of genus 1. The isomorphism curve of the isomorphism type of the curve is fixed also for some of these groups, so there's further restrictions. Okay, so back to the number field case. So if we have a field K, we want to know what are all the possible torsion subgroups that happen for a fixed field K. And that can happen already. We have full classifications for specific fields. Philip, who is back there, he proved, for instance, that that if you fixed just Q adjoint I, so let K be Q adjoint I, then you can come up with a full list of what torsion subgroups can happen in that quadratic field. You can also change all quadratic fields, so you can now vary all quadratic fields and look for elliptic curves over quadratic fields and see what happens. And then that was improving on the techniques of Maser, on the formal immersion techniques. Kenku and Momose and Kameani, after a long series of papers narrowing down what the possibilities can be, they finally proved the full classification of what can happen over quadratic fields. Of course, not everything can happen over every quadratic field. For instance, if you see Neimann's result here, there cannot be a full 3 torsion defined over K if K is Q adjoint I, again because of the Weil pairing restriction that you would have to have the 3rd roots of unity in your field. So for instance, here you can see that there's full 3, full 4 torsion, but not both can happen in one quadratic field. But this is the whole list you can find over quadratic fields. Here, there is also infinitely many, whenever I say that each torsion subgroup occurs infinitely often, what that means is that there are infinitely many different J invariants where each one of those groups appear. So in here, the modular curves that are parameterizing the structures, they are not all genus 0, but there are at most genus 2, therefore hyperelliptic, and there will be infinitely many quadratic fields where there are points. So you can also find these infinitely many examples. And there are pictures of Kenku, Momose, and Kameani. And so for instance, now you can find something that doesn't happen over Q, a point of order 13. In Q adjoint the square root of 17, there is one point of order 13, for instance, that one. You can parameterize x1 of 13, and then you can find the J line for that and find all the examples you might want to look at. And here is a picture of that. Since it's since the curve is defined over the real numbers, and you can actually do a real plot of that, and it looks nice. If you are keeping track, there are 10 points in that picture, so you have to go a little farther to see the other 2, the 12 and then the 1 at infinity. Okay. There are other ways you can find points of order 13. That was a point of order 13. This one is a point of order 13 over a quadratic field. they don't happen just in quadratic fields. You can also find them in other places. For instance, this is an elliptic curve that has a point of order 13 over a cubic Galois extension. So they also happen sort of naturally in cubic extensions. And this example is also nice, that the elliptic curve is defined over Q, and then base extended to a cubic, and then I find a point of order 13. So that will be a theme. We'll come back later on, where I'm sort of from elementary number theory applications, we're more interested in elliptic curves that are defined over Q, and then see what can happen when you base extend. So we've done quite a bit of work also in that subfamily of elliptic curves.
I have a question.
Yes.
Is the subgroup generated by the point rational in that case?
The
subgroup generated by this point of order 13, is it rational?
Yes, yes. It comes from an isogeny. So this elliptic curve has a 13 isogeny, but the field of definition is very small. Yes. That will be also a theme, especially in the case of elliptic curves over Q, that we are trying to find points of prime order that happen early on, meaning in small degree extensions. And when you're working over Q, then it's convenient to look for isogenies where the field of definition may be particularly small. Okay, so you can also now think like in the Kameyani-Momose-Kenku theorem. So what happens if we go over all cubic fields and all elliptic curves over cubic fields? What's the classification there? And this was done in a couple of stages. So first, Guillaume, Kim, Schweizer proved which ones can happen infinitely many times. In what modular curves there were infinitely many points. So that was done first, but we didn't have a classification of all the ones that may happen only finitely many times, which we will call sporadic points. So here's pictures of Guillaume, Kim, and Schweizer. Actually, Nyman also realized that that classification could not be complete over all cubic fields because, there is actually one elliptic curve. So it turns out that there is an elliptic curve over Q where over a cubic extension, that is the maximal real subfield of this cyclotomic field that's cubic, and there is a point of order 21, which is not in the list that appears here. So this must be an example of an sporadic point where it does not happen infinitely many times over cubic fields, but there's a finite number of examples of J-invariants where this must happen. So that classification cannot be complete. There is at least one more subgroup. And recently, there's been a double announcement of the full classification where Tropolsky, Morrow, and Zurich Brown and Martin Diereks independently have classified all the possible torsion subgroups over cubic fields. That classification is actually, so the one that happens infinitely many times, and Nyman's example of Zimot 21, and then that's it. So now in this case, Zurich Brown in particular has an amazing talent for finding points on modular curves, and their method relies on really, well, first we knew from work of many people what restrictions there might be on what primes might appear as orders of torsion points in cubic fields. So with that restriction, you can write a finite list of modular curves where we would try to find these points, and then there is there's a lot of new techniques, all the new techniques on finding those points and what of those curves have points and which ones do not. Something that, if in this particular case, it's something that Zurich Brown calls the Mordell-Weil sieve, which is very interesting on its own. Okay, so what do we know about quartic, quintic? So quartic we know now. well, no, I mean cubic we know, but for about for quartic, quintic, sextic, and beyond, we don't have a complete classification. That's where the game stops. We don't know what are all the possible subgroups that can appear over quartic fields. But we do know over quartic, John, Kim, and Park, we know the classification of those that will appear infinitely many times, and that's the list. And Dirks and Sutherland have also shown what can happen over quintic number fields infinitely many times. Again, these are now trying to find what modular curves will have infinitely many points, and those are easier to classify than trying to understand all the rational points and all the possible modular curves that are involved in this problem. I should say that we also now know, I believe, what primes can appear as prime orders for quartics or quintics or sextics, and maybe for, or at least a good bound for degree 7. So that reduces the number of modular curves that you have to look at. And Dirks and Sutherland, they also have a classification of what can happen over sextic number fields infinitely many times. Okay? The case of elliptic curves with CM deserves its own category because the theory of complex multiplication allows us to do much more. The torsion, because of the class field theory interpretation of torsion subgroups of elliptic curves with CM, it allows you to go quite a bit farther in the classification. So for instance, in 2013, the Clark machinery of Clark, Korn, Rice, and Stankiewicz, they created an algorithm to actually compute the possible torsion subgroups by degree, and they classify completely up to degree 13 in their paper what are the total lists of possible subgroups that can appear if you are working over a number field F degree D up to 13, but the elliptic curve has CM. So for instance, so over Q, these are the groups that can appear, not the full list of Maser can appear, only a few of them. Over quadratic fields, or elliptic curves with CM defined over a quadratic field, you have to add those many groups. Over quartics, you get this list, and so on. And they have the explicit lists are in their papers. You can also do more, and very recent work of Abbey, Burden, and Clark. They have the following kind of theorem where there is an explicit constant. So for an elliptic curve over a field F, and you have CM by an order in a quadratic imaginary field, which for the sake of the theorem here, I'm including it in the number field. Then there is a constant such that if there is a point of order n in the torsion subgroup, then TON, that constant, divides the degree over the class field or the class the class field for that J invariant. So it tells you how far you would have to go. So if you have an extension that is too small, then you're not going to see points of several orders or orders bigger than what the bound gives you. And in fact, this is best possible in that there are elliptic curves where there are points of order n defined exactly in extensions of degree T of ON. By the way, so as I said, I'm concentrating on elliptic curves mostly, but Davide Lombardo, who is somewhere here, I don't see, no, there he is. He has also amazing results on this vein, but for abelian varieties. So he has bounds on, for instance, the full L to the n torsion. If you take an abelian variety over a field F and you want to see the full L to the n torsion, what is the actually an upper bound and a lower bound where these field of definition will be found, and also some other results about if you apply those results to elliptic curves, then he also gets similar results to what Borden and Clark obtain. I should also say that, so now we've switched in that for elliptic curves with CM, as I said, there is several approaches. You can use classical theory, but you can also just look through classical theory or not. You can work with the Galois representations that appear, so the modulo n Galois representation. You can have a very nice description of what that Galois representation is, and then through that figure out what the field of definition of these points are. Okay, so as I said, now we're going to switch gears, and we're going to treat a case that may be a little more interesting for some, or definitely is just a simpler case to work on, is if you start with your abelian variety defined over Q. If your abelian variety is defined over Q, then you have more techniques that you can use. There are more techniques at your disposal. For instance, if you have an elliptic curve over Q, then, for instance, we have the complete classification of what Q rational isogenies are there. And that's a huge improvement over any other number field. We don't have that classification. For instance, one student of mine, so Harris Daniels and I tried to classify just 37 isogenies for elliptic curves over Q at joint I. And that is already I believe it was a genus 3 curve that we just could not find the rational points until like recently. There is some methods of Balakrishna and her collaborators. There is some, this sort of like two-dimensional Chabot where they've classified what points are there in that rational, in that modular curve. So it's, yes?
You mean that Chabot does not apply to x0 of 37 over Q of I, that's right?
Yeah, so sort of like classical Chabot does not apply, and you have to use one of these new non-abelian Chabot methods to be able to classify all the points on that rational curve, on that modular curve. Yeah. So we're interested in, now. The restriction is now that we are working on elliptic curve over Q, and then we want to see what torsion subgroups happen as you base extend to different number fields. So myself, I showed in 2011 what primes can appear as degrees of points of order P. So if you write S1 of Q of D for the primes, such that there is an elliptic curve over Q and an extension of degree less than or equal to D of order P, then you can classify what points can appear by degrees. So up to degree 2, you only see points of order 2, 3, 5, and 7. To see a point of order 3, you have to go to degree 3. Remember, we saw an example of an elliptic curve defined over Q that you base extended to a cubic number field and saw a point of order 13. You cannot do that over Q and go up to a quadratic and see a point of order 13. You have to go to a cubic. So that's what the list says, and I just worked out what can happen, in fact, up to D equals 42. And there is, in fact, a conjectural formula for all of for all these sets, which is Serre's uniformity question, which I won't go into describing. So we have a good idea of what Galois representations, the mod P Galois representations, can happen for elliptic curves over Q. And we have a good idea of what images can happen. So if all the images that we think happen is that those are the ones that happen. So there's a question, the one that remains is whether there is infinitely many elliptic curves where there will be, or whether the image can be in a non-split Cartan infinitely many times for a larger P. If that doesn't happen, then this formula gives you the complete list of what primes can appear. All right, so then sort of like generalizing that work with Enrique González Jiménez, we studied what are also the degrees of definition of torsion subgroups, so not just the minimal degree of definition of a p-torsion point, but degrees of definition of torsion subgroups. And we have bounds or lower divisibility bounds on what are the degrees of definition for each one of these torsion subgroups, which would also be best possible if you assume source uniformity. For example, something that comes out of that is that if you have an elliptic curve defined over Q without CM, and you want to see a point of exact order 2 to the n, then the degree is divisible by 2 to the n minus 7. And this is the best possible in that there is a family of elliptic curves where that happens. There's a point of order 2 to the n, which the degree of the definition is exactly 2 to the 2n minus 7. And I should say, so here the methods is just relying solely on the Galois representation. For instance, in this case, we exploited the fact that Jeremy Rouse and David Zurich Brown classified all the possible two-adic images of Galois representations attached to elliptic curves over Q. So that's what I thought was an amazing result. I went on sabbatical, I brought their paper and said, okay, I think it's an amazing result. There should be a lot of consequences that one can draw from this. And there are lots of things you can do about, basically, since we know all the possible two-adic images, you can figure out everything about two primary parts of elliptic curves over Q. And this is one such consequence. Then if you want to study the question, okay, so what happens then now by degree? So if I start with an elliptic over Q and then base extend to a quadratic number field, then Nyman classified all the possible torsion subgroups that happen over quadratic fields starting from Q. And he also classified all the possibilities that can happen over cubic number fields starting over Q. And here is where he found that example of where so all the torsion subgroups happen infinitely many times except this one, the 21, which is the one we talked about before, that only happens once. Okay, so now the question is what can happen over quartic fields? Over quartic fields, Mike Chow, who was a student of mine, he started that problem by classifying what can happen over Galois quartic fields. So if the field is quartic and Galois with just a billion Galois, then he classified all the possibilities. What can happen, in fact, he has a theorem for what can happen over Z mod 4 extensions and what can happen over Klein 4 extensions. Of all the torsion subgroups that can happen. Then trying to move forward to a complete classification over quartic fields starting over Q, Enrique and I proved what can happen infinitely many times. Now there's two different lists you can come up with. There is a list of what happens infinitely many times over quartic fields, and of those, what can happen over Q, and then also what happens over Q infinitely many times. So there's two different situations there. So we listed both what can happen infinitely many times over Q and what can happen infinitely many times over quartic fields and also over Q. So for instance, then now there is like split of cases where, for instance, Z mod 15, which appears infinitely many times over quartic fields, over Q, it only happens finitely many times. So these will only happen for these many, 4 J invariants. You can see Z mod 15 by base extending to a quartic. And then Gonzalez, Jimenez, and Nyman have finished off based on Mike Chow's results and my result with Gonzalez Jimenez. Then now they've actually finished the classification of what can happen over quartic fields is starting over Q. Remember that we don't know what happens if you start with an elliptic curve which is already defined over a quartic. That we don't know. But if you start over Q, then you can figure out what's the complete classification. And furthermore, they develop some new kind of machinery where they can actually determine what are the possible prime orders of a point, as long as you have, for all degrees up to 3 million and change, they can figure out what all the possible prime orders are that can happen when you base extend. So, so far, we were base extending from Q to a finite extension. But you could think about, in our variations, you could think about going up a tower of finite extensions and then see what happens at the limit. So what happens over an infinite extension? And well, the question now is that the Mordell-Weil theorem does not apply anymore. So the torsion subgroup, if you go to have infinite extensions, certainly if you go up to Q bar, the torsion subgroup will be infinite. So what can happen in an infinite extension, you have to be careful which infinite extension you pick. So we're going to be talking about going up in a tower of number fields and see how the torsion is growing. And we are interested in cases where over an infinite extension, you still have a finite torsion subgroup. You might have an infinite free part, but we're interested in how the torsion is growing. The first example of such a theorem was a classification that Laska and Lawrence started in 1985, and then Fujita finished in 2005, where if you take the maximal to elementary abelian extension of Q, so Q adjoin all the square roots, then it turns out that that torsion subgroup for an elliptic curve is finite, and you can classify what torsion subgroups may occur. One sort of like the, if you think again from, since we know we have a very good idea of what the mod P Galois representations are, we know from Sayre's open image theorem, the Galois representation modulo P will be surjective, will be GL2 of Fp for infinitely many P, then you expect that over quadratic fields, there's only going to be a trickle of primes where you might see some extension or some growth in the torsion subgroup. So this is something that it should be expected, and it should be expected for sort of like horizontal infinite fields. If you take infinite fields which are a composite of degree D extensions and over Q, then you wouldn't expect the torsion to be able to grow because of just the image of the Galois representation being large. So, for instance, I invited Philip to come visit me a few years ago, and Philip came with the question. He had just proved the classification of what can happen over cubic fields for elliptic curves base extended to one cubic field, and he thought that we could do the classification over the compositum of all cubic fields. What are the possibilities there? And it took a little more work than we originally thought. That's Philip and I yesterday. And in a hike. So Harris Daniels, Harris, who is one of my students, my first student, Drew Sutherland, and Nyman. So we classified all the possibilities for torsion subgroups. And here, there were a bunch of modular curves that were quite involved to get our hands on all the rational points. But to my surprise, we were able to finish the classification. In that vein, there is, you can, as I said, you can do horizontal extension. So Daniels has classified all the possible torsion that can happen if you do the compositum of all D4 extensions. And Daniels, Derricks, and Hadley, that they've classified all the torsion subgroups that can happen over the compositum of all A4 extensions. And they have results about sort of like QG infinity. If you take all the Galois extensions that have Galois group G, and then you do the compositum of all that, they have certain results and the classification of torsion subgroups that can appear in that case. That's Jeff and his llama Nimbus. Okay, and that's Colton.
That's the name of
Nimbus. Yes, the Nimbus the Llama has its own Instagram account. Yes. Okay. So what other infinite extensions you can think of? Probably one of our favorite ones would be the infinite abelian extension or the maximal abelian extension of the rationals. In there, we actually have a finite generation theorem by Ribet. He proved that for any abelian variety over Q, if you base extend to the maximal abelian extension of Q, the torsion subgroup is finite. So there's a question there of whether if you now vary over all abelian extensions, whether that set of isomorphism types, that will be finite. Zaren, he extended Ribet's theorem in that if you take an abelian variety over a number field, and then you take the maximal abelian extension of the field of definition of the abelian variety, then that's no longer true that that the torsion will be finite, for the simple reason that if you start, for instance, with an elliptic curve over Q, has Cm by K, if you base extend to K, then you will see that, for instance, all the split primes there will be a lot of abelian extensions with points, with torsion points. So as long as the field of definition does not have there is no abelian subvariety with Cm over the base field, then you will not see those points over an abelian extension. In the case of Q, most of the points will be over some dihedral extensions or generalized dihedral extensions, so you won't see it over the abelian extension of the base field. But so looking at abelian extensions, Gonzalo Jimenez and I, we proved, for instance, if you start with an elliptic curve over Q, you know that the n torsion, so this is the field of definition of all the n torsion points of your elliptic curve, at least it contains that, again, by the restriction of the wave pairing. So you could think of the question of, like, when is it exactly that? Because that's the smallest it could possibly be. And it turns out that that is an open problem over number fields. So if you start an elliptic curve over K, when is it true? For what cases, even for primes, when can the P division field be K adjoin the P roots of unity? That's an open problem, which is only known for a finite number of primes when this can happen. So that's not known in the general setting, but you can do it over Q. So we prove that these can only happen when n is 2, 3, 4, or 5. And again, exploiting that classification of two-adic images by Rouse and Zurich-Brown. You can also think like, well, okay, maybe it's not just that, but it might be abelian, and that you don't gain a lot more. It can be n can be 6 or 8. The n division field can be abelian, and you can also classify what abelian groups happen or as Galois groups of n division fields. And then my student Mike Chow, also as part of his thesis, he completed that theorem of Ribet in that he classified what torsion subgroups can happen for elliptic curves over Q abelian. So first of all, the torsion subgroup cannot be bigger than 163. The bound is sharp because there are elliptic curves with a point of order 163 over Q abelian. And he gives a complete classification that I will not write here. All right, so now let's move on to higher degrees. So we are going to take, now we're going to vary fields of degree D and then elliptic curves over fields of degree D. In that case, of course, there is what was called the uniform boundedness conjecture, was proved by Morel, in that there is a bound such that the torsion subgroup is bounded by this bound B of D for all elliptic curves over E over F. Now, what do we know about that bound? Well, from Mazur's theorem, for degree 1 it's 16. For degree 2, from the Kenku Momose Kamiyani theorems, that bound is 24. And there is a conjecture, folklore conjecture, that there is a constant such that the bound is lower than d times log d for all d bigger or equal to 3. What do we know about that bound? So Henri and Silverman showed that, for instance, if you have a field of degree 2 or more, an elliptic curve where the j invariant is an algebraic integer, then you have some sort of bound of that type, that the torsion subgroup can be bounded by constant times d log d. There were other results of this type by Flexer and Osterle. They have also results of this type. If you have a, I believe, if you have a 1 prime of additive reduction, then you have some bound of this sort. If you have 2 primes of additive reduction, then actually the whole bound is constant. So there is some results of that type. And then recently, Clark and Pollack, again, concentrating on the case of CM curves, they've shown that if your number field of degree d bigger or equal to 3, then the whole torsion subgroup can be bounded as predicted with d log d. Now, we also get out of that bound, I've talked a lot about before about what can happen for primes of prime orders of torsion points. Now we also get out of this bound, you get bounds on the prime power orders of primes that may appear dividing torsion subgroups. And as a consequence of Merel's theorem, there is a bound on, like, for instance, if there is a point of exact prime order p to the n, then p is less or equal to d to the 3d squared, and then parent improve those bounds to have, but it's still an exponential in d, and we're hoping to find bounds such as in the conjecture, where those bounds are linear in d. So I had some work done in that direction, in that what I tried to show is that in many cases, the bounds that appear in the conjecture, or the bounds that appear, for instance, in Henri and Silverman, those bounds are not just on the degree, but actually on ramification indices. So you can bound the torsion subgroup, or the bound of order of prime power orders by the torsion, by the ramification index of your number field. That's sort of like the analog of if you take if you take a number field where there are roots of unity in that number field, then you know there is some ramification. If there are p to the nth roots of unity in your number field, then there will be ramification at p in that number field. Analogously, I believe that in elliptic curves, if you see points of prime power order, there will be ramification in the base field for most primes. So if you take what I called Emax in an extension of number fields, the largest ramification index above p for a prime of L up to f, then I showed, for instance, that if you take an elliptic curve for a CM, with CM by the full order, then you see that phi is the Euler's phi function of p to the n is bounded by sort of like the degree, but not just by the degree, but by the ramification index at p, or the maximum ramification index at p. And of course, the ramification index is a finite extension, so that ramification index will be 1 for all but finitely many p. By the way, so as it is, this is worse than other theorems that are known by Prasad, Yogananda, Silverberg, theorems of Lombardo, or Clark and Borden. So this is actually, you can do better than that. I believe you can do at least 12, and if p is bigger than 3, you can do a 6 there. But so the interesting part is that you can actually bound it by ramification indices. And more generally, so without CM, if you have an elliptic curve with at least one prime of potential good supersingular reduction, then you can bound and there is a prime, there's a point of order p to the n, then you can bound this power of p by, again, some ramification index and also the max ramification index and the degree. Okay, so that led me to conjecture that in fact that always happens. There is some constant c where you always have this bound of the Euler phi function of p to the n is bounded by a constant times the maximum ramification index. So you can also think about the question of now try to get more mileage by going in extensions of the base field. And in that case, so if you start with an elliptic curve over Q, and then you base extend to a point to a degree D field, then we actually have a result that there is still a bound on the ramification index that is linear on the ramification index. And if you go to number of fields, if you look at all the elliptic curves defined over a field F, and then go in extensions, when you will see points of order p to the n, that's bounded by, again, a constant that depends on the field F. Unfortunately, I cannot remove the dependence on the base field F, but then there is a bound that is linear on the ramification index of the extension. And moreover, except for a finite set, which you can determine for every F, you can actually compute that constant, and for instance, 588 works for any field. So I just wanted to finish with something, some other recent result on the now abelian varieties. So David Zywina has proved what's called the Henri-Rattata conjecture for as long as or subject to the Mumford-Tate conjecture for abelian varieties. So so let me start here. So the Henri-Rattata conjecture says it gives a definition for what is the smallest real value, such that for any extension L over K and any real number epsilon, then we have that the full torsion grows as a power of gamma of the degree of the extension over K. So and then so the definition of gamma A is technical, and I won't go through it, but that's some result in that direction also of trying to bound the size of the full torsion subgroup with under base extensions in terms of linearly or as linearly as possible in terms of the degree of the extension. So I think I'll stop there. Thank you.
To repeat, you need to ask questions in the microphone. Any question? Well, I have a question. Of course, you presented a list of possible torsion subgroups for various number fields of a certain degrees. There are cases which occur infinitely many often, and others which are exceptional. And about the situation which occur infinitely many often, I think the answers are guided by this notion of gonality of modular curves, and to what extent actually do your data correspond to what we can see from the gonality of those curves? So
there is a lot of work on this, on sort of like gonality bounds and the sporadic points that I haven't discussed. But it's still quite unclear what is the best sort of like the gonality bounds, and then what can happen sort of like for sporadic points. So there is some tables, for instance, I think in Martin Derek's website, there is a table of sort of like what is known for the sporadic points, where it's the lowest degrees. So we don't know, I don't think we know any lower bound even for sporadic points also. So there's a gonality bound, and then lower bounds for sporadic points are still not understood what can happen.
More questions?
So Silverback has a result of counting rational torsion points on CM abelian varieties. Applying to curves, does that give a bound in terms of d log d or d to the power of 1 plus epsilon?
I'm not sure I'm familiar with that result.
Alice Silverback.
I'm not sure.
I'll check. Okay.
Yeah, if you could let me know, we can talk after. If you can show me.
Okay.
Thank you.
Okay, let's thank the speaker.
Thank you.